Okay, today we covered three basic topics. The first of these was the definition of the velocity field. The velocity field is a description of the fluid motion, which is really quite complete. It takes the velocity vector v and describes how it varies in x, y, z, and t, all three spatial dimensions and time. The velocity vector v is itself made up of three components, u, v, and w. So the specification of all of these in space and time constitutes the velocity field, and it's really the most complete description of the velocity of the fluid. Now, in certain cases, the velocity may only vary in one dimension or may only have one component, or it might just be a useful simplification of the velocity. In that case, I'm going to refer to a velocity profile, where the velocity profile tells us that the velocity vector only has one non-zero component. Well, I'll say that's the u component here, and that component only varies in one dimension, say u of z. Now, it could also be a function of time in the case of unsteady profiles, but in general, we'll usually talk about steady flow and use that as our starting point in thinking about velocity profiles. Next concept we talked about was the viscosity. I forgot my C. Viscosity. The viscosity is the stickiness of the fluid. It's this internal relationship between the shear stress in the fluid and its velocity gradient. The larger the viscosity, the greater the stress is within it. So if we have a velocity profile, which we've just defined, say u of z, and we want to define the shear stress in the interior of it, tau, we relate tau to the velocity gradient through the viscosity. And the viscosity here I'll put in red is defined as minus mu, where mu is the absolute viscosity. So that is the viscosity of the fluid. It's this proportionality between the shear stress and the velocity gradient. Final topic, I should note that in non-Newtonian fluids, mu is not a constant, but for most of our cases, mu will be a constant, making it Newtonian fluids. Final topic that we talked about today was surface tension. Surface tension is a force in the plane of the interface between two fluids. So it acts in the plane between two fluids. Think of it like a layer of fabric that sits right on the interface between these two fluids. And the easiest one to think of is air and water. So along the air-water interface, which I'll denote with this upside-down triangle, the example I gave in class today was if we tried to pick up a little parcel of fluid, then the compensating surface tension force, which I'll show in blue, acts to try to pull that back down. Now the surface tension force, F sub sigma, is given by the surface tension parameter sigma times L. L is the length over which the force acts. Or along, maybe I should say along which the force acts. We did an example in class today of capillary action in a tube. It was the perimeter, or the circumference of the tube that is L. In this case, L would be, in this example that I'm drawing here, L would be the circumference around that parcel that we're picking up. Sigma, as I said, that's the surface tension parameter. It's the one that you look up in tables, and it's a function of the particular fluids that you're considering and the temperature. So you'd look it up for the air-water interface. All right, I think that's it for today. I will see you all on Wednesday.